Thanks, Julia. And I really want to give a note of gratitude to Julia for really helping us out, getting this organized through the whole process. She's been great. And I want to introduce my co-conveners, Steve Sebestyen with the Forest Service in Minnesota, Theresa Blume at the German Research Center for Geosciences in Potsdam, and Julia Jones at Oregon State. I wanted to say a few words about how we got to this point, this seminar series with, I think Julia forgot to mention how many participants we have. Over 300 have registered for this, so a really great turnout. And this all came about through a series of AGU sessions on long-term catchments or catchments in general that Steve Sebestyen started and that I joined in at some point. And it culminated at the AGU 2019, where we had 70 posters in an all-day session that really just was a great experience. There just was so much camaraderie and a community spirit for catchment science there, and that sort of prompted us to launch this special issue in hydrological processes, where we have well over 100 papers, and that's coming. Many of you have contributed to that, which has been great. Will you want to put up the map now, Julia? So in the process, we've developed this world catchment map. I guess I skipped a few things, but so this shows all the catchments that we've got coordinates on, and this is still growing, and there's some gaps that we just didn't quite get to, like Australia has some research catchments. Africa has a few more than is shown. South America does too. The red dots are the presenters of today. We wanted to get a kind of a geographic diversity here. And go to the next slide, which has all the red dots here are the catchments that are included in the special issue in hydrological processes. So really a great, worldwide coverage there. And go back to the last map. Actually, go forward, Julia, to the picture of the broken down stream gauge. There we go. This is from my watershed. And Steve Sebestyen actually superimposed this on actual data from this site. And this is about just, a lot of catchments have funding issues. Part of this whole series is to try to keep the whole catchment enterprise going. How can we keep it funded? How can we keep it relevant? You all are going to have great ideas on this, and then we're going to culminate in week 8 on a brainstorming session on how to keep going. Next slide. I just wanted to touch on the history of, catchments. Started at Wagon Wheel Gap in 1919. Here's an old vintage photo. And, a lot of this earlier work came on, was motivated by forest harvest, effective forest harvest on water yield. And we're going to have a whole week session on that later on in the series. And just want to say that before handing it off to my co-conveners to say a few words too, if there's time, that catchment science has influenced policy. My example is in my neck of the woods, Hubbard Brook in the Adirondack. Acid rain research has really helped shape policy on the Clean Air Act and subsequent Clean Air Act amendments. So with that, I want to pass it off to Steve and Julia to say a few words. I think Steve was going to be up first.
Yeah, so thanks. It's really great to see the community coming out. And I guess that's one of the rallying points that I want to start off with, is that this session is for all of us, and it's to really try to spawn more interactions and a recognition that, we are so heavily invested in our own sites that sometimes we forget that there are all these other catchments out there. And consider the geographic breadth, the climatic, the vegetation types, as well as the cultures and the people who work and learn from them. So I hope it's just a call. Jamie showed the picture of a broken down gauge house of an abandoned research watershed. And we know that's going to happen to some sites, some places, but if we work together, we come together and we pool our resources and our ideas. That's what we really want to gear towards with this synthesis, new ideas, how do we move forward from old sites and legacy data to the best science, the most relevant, and how does that feed back on ecosystem management and the political atmosphere that by providing information, we can be influencers on that. So I guess that's really where I want to stake a claim in this whole thing is embrace your fellow catchment scientists, embrace the sites that you don't know about. There's a jam-packed schedule. It's intended to cover as much ground as we can. It's also an attempt to equalize from the best known studies out there to some that are just starting out and have almost no recognition. So with that, I also just do want to acknowledge so many of you have contributed to special issue for hydrological processes. Thank you. You're putting your catchments on the map that is being shown here, and all the red dots. That's our representation, the global coverage in this issue. We're looking forward to getting these moved on, published, and again, just thank you for what you've done to help us with this.
So Julia, I know we're running out of time, but I know you want to say at least one thing.
Thanks, everybody. Thanks for joining us. Many of the important points have already been made, but it's just a reminder to us all that long-term catchment studies, however short or long they are funded by governments and industry, but many are cobbled together by small grants. And while they were originally started with certain questions in mind, particularly the ones in the early 20th century that were focused on forestry and agriculture. The beauty of catchment studies is that they are continually open to new questions as our world and our society evolves, and many of the talks today will demonstrate that. And this effort is really an effort to build community, not just the community that you can build within your catchment study, because it gives people a place to collaborate locally, but across catchment studies internationally, particularly in a world where we are facing in accelerating global change.
Thanks, Julia. And if you could bring up the slide that shows today, you can skip this and go to the schedule for today. I just want to elaborate one point that we really designed this to be all inclusive, not just the well-known catchments, but we wanted to let everyone with a catchment in on this. And it means that some of you will only have 6-minute talks in this, but we wanted to be all inclusive. And we're going to find out about catchments we never heard of, and it's all going to help us, I think, continue this whole enterprise into the future, find ways to collaborate and work together. And so we'll start off today with Tim Burt talking about some very long-term data sets. Take it away, Tim.
Thanks very much, Jamie. The organizers encouraged me to talk about long weather records, which might not immediately seem relevant, but I think they are to catchment watershed scientists. And my alternative title just stresses two things. The first one is to be curious. It's about curiosity and the importance of these very long data sets and what they can do for our science. Two photographs show on the left the Durham Observatory, which has weather records from 1841, and the Radcliffe Observatory at Oxford, which has records from 1767. So they're both very long records. Next, please. And my message above all, I think, is that long data sets allow us to be curious, and that this is where we may look for new hypotheses, as well as looking for data that will help us confirm our ideas. But I'm a great believer in new hypotheses and the whole business of curiosity. Next, please. The Oxford Weather and Climate book on the left came out in 2019, written with somebody with the same surname but no relative, and we're hoping that our Durham book will come out next year, same authorship. Here's my son on June the 4th, 2000, the biggest flood on the River Weir, which runs through Durham, and then a week later the annual rowing regatta. And you know, there's what we're interested in: high flows, lower flows, and so on and so forth. Next, please. Well, what do these long-term data sets allow us to do? They allow us to look about changing environmental influences and system behavior, and they provide evidence of change or not. And I think that long data sets are particularly useful for studying weak signals in noisy records. You need a long record to be able to work that out. They tell us about rare events and episodic phenomena, and they often tell us about sort of episodic behavior. Next, please. So we might ask the question, well, so what? If you happen to be a master's or a PhD student sitting out by a river collecting data over, say, 12 months, you may look at your record and say, so what? What can I see about longer term change? If perhaps you had 4 years, 48 months, you might begin to say, there's some seasonal cycles here, and that might raise some questions. If you have a longer record, like say 7 years, 84 months, you might begin to see that there might be some unusual behavior. And if you have a very long record, 30 years or more now down at the bottom, you can see maybe evidence of long-term trends. So long records uncover processes and trends that we may well be interested in. The unusual years is a post-drought series of very high DOC episodes in autumns that followed a very extreme drought in 75, 76. Next, please. So here's Durham's mean air temperature record since 1850. The green line gives you a running mean and annual mean air temperatures, maximum and minimum from 1900, when we've got more reliable Stevenson screen records. I put the one in at the bottom because as part of writing the book, we've done some extension. So here's one of Ed Hawkins' climate stripes taking Durham annual temperatures back to 1795. And there's evidence, obviously, of variability, cold, very cold periods in the early 1800s, the 1840s, the 1870s and 80s, and of course the remarkable warming of the last few decades. Who couldn't be interested in that sort of long-term change? Next, please. And of course, not only do we have temperature records that might be useful for evaporation studies, we've got long annual precipitation records. No particular trends here as far as I can see, wetter and drier periods, and no trends as far as one can see in the annual maximum daily fall, but they're still interesting long records. Next, please. And if I want to look at the River Weir, which you saw earlier in flood, I perhaps don't use the Durham record. I use one of the gauges up in the hills. I say only got records, discharge records for the Weir since 1958. That sounds relatively short compared to Durham's rainfall from 1850. But of course, that's still a good long record, over 60 years, and of interest in its own way, wet periods, dry periods, and so on. Next, please. The famous American geomorphologist, William Morris Davis, often thought of as a rather sort of staid scientist, but he used to encourage outrageous hypotheses, people to put forward ideas and then see if they could prove them. So here's one outrageous hypothesis for you. Has Oxford winter rainfall been getting wetter for the last 250 years? There is a long trend there from the 1770s. I've not done very much work on this yet, but it's intriguing, and that's what we should be when we look at our data. We should be intrigued by what patterns we see show up. Next, please. And of course, there are other long records. It doesn't have to be rainfall and runoff. Here happens to be a long nitrate record, the longest in the world, I think, for the River Thames, that some of us worked on and published, and this has been updated. Something strange is happening in the last few years. I'm not quite sure whether that's to do with changed sampling or what it might be, but new questions arise. Next, please. So why is long-term monitoring important? The data reveal important patterns for us to explain. They may be essential for testing hypotheses undreamt of at the time the monitoring was set up. For example, the impact of acid rain on DOC export. And of course, monitoring is a vital way of discovering whether we've got significant undesirable changes taking place. So these long records are really, really important. Next, please. And monitoring sometimes is considered a rather dirty word. People talk about mindless monitoring, but I think it's perceptive science. Having that maintained record allows us to delve in and investigate, and we shouldn't think of monitoring as unimportant or mundane. And I think last, please.
Thank you very much, Tim. I'm going to be moderating the chat session, and at this point I can say that nobody has chimed in. So I will encourage everyone to use the chat box to address their questions to panelists or to the overall discussion at the end. So please keep that coming. But Tim, one of the things that strikes me is that you're playing a tremendous role as not just a hydrologist, but an archaeologist in here too. And can you comment on that aspect of it in terms of how do you become aware of these records, and then how do you go about getting them and then doing the QA/QC? Because that's a massive task.
Absolutely. Well, of course, I'm aware of these two weather stations because I was lucky enough to run the Oxford one for 10 years. And now I've been running the Durham meteorological station for the last 20. And what you find is, yes, some of the data has been digitized, but a lot of it is still in manuscript form. And you've sometimes got to go back to original ledgers and find the data and get them transcribed. There's quite a lot of citizen science going on these days where people are prepared to, say, transcribe a year or two of temperature data or whatever it may be. And there will be records, maybe not quite as long as this, but, you know, late 1700s, early 1800s, there will be weather records, particularly in the eastern part of North America, and some of those will be sat there waiting to be explored. I know it will be a bit more recent when you get over to the west, but nevertheless, there are these long records available that go back longer than somewhere like Wagon Wheel Gap. It may be that, you know, those weather records are a good place to start if you're trying to, say, put some of these changes that we look at more recently into a longer term perspective.
Great, thank you very much, Tim. Still somebody is making a comment about the monitoring and long-term data sets being important for modeling and verification studies. Do you have anything to say on that quick before we move on to our next speaker?
I think that's absolutely right. And these records are really important if you're looking at long-term climate change and the impact on hydrology. Of course, they help us to verify our models. And out of that comes new questions because things won't work out quite as we perhaps hoped or expected they might. So I wasn't trying to belittle theory verification, but I'm just encouraging people to be curious and look for new patterns as well as trying to test established hypotheses.
Great, thank you, Tim. Jamie and Julia, I think we should move on. Just let me remind all participants, you have the opportunity to engage through the chat. Please keep questions, comments, and a dialogue running here, and we'll do our best to cover it.
Yeah, thanks, Tim. Great talk, really interesting. And now we're going to move on to Manfred Staley and Ilya van Minnerveld, and we're going to move to Switzerland. I think Manfred's going to start off.
Okay. It's my great pleasure to welcome you to Switzerland, to the Alps. It's a different environment. Next slide, please. You see where this next catchment is located. It's in the heart of Europe. That's a hilly region between 1,000 and 1,500 meters above sea level. And actually, it's also the region with the highest precipitation in Switzerland. So very interesting for hydrological research. It's about 30 kilometers southeast of Zurich. Let's have a closer look at this catchment called Alptal. Steep slopes. We have beautiful headwater streams with a step pool topology. And here you see a first glimpse to the long-term hydrological infrastructure of our team. For 50 years, we have done research here in the Alptal, and maybe these are central pillars of this research catchments, characteristics that are important for this research here. We have very wet soils, clay soils, and that leads to dynamic streams. We have, for example, at low flow, we have hardly any flow. And if we have a big flow, it can be 15,000 liters per second. So a very dynamic system. What is also interesting is the heterogeneous forest. And as a snow hydrologist, I'm also very much interested in this variable snow cover, which can change from winter to winter very much. Next slide. A few words about the history of this research. Everything began in the 1960s. It was this guy in the center that you see, Hans Martin Keller and his team. He was the driving force and the research leader for almost 3 decades. And he had also hard times. For example, in 1974, all his runoff stations were destroyed in one single storm event. Obviously, these stations were not solid enough built. As you can see from these images, the role of forest with regard to flood events was also a key topic for these researchers. But also from the beginning, water quality was an important issue for these researchers. We have monitored these streams with regard to water quality for almost 50 years. We have also a lot of research on snow. This was, of course, of great interest in this heterogeneous vegetation. And today, we can say that these catchments have developed from more monitoring side to a very interdisciplinary research community. It's a hydroecological program that is running now, and that's also our strategy for the future. Next slide. And you see it has become a true collaboration between different institutions, and this is clearly a playground for many different aspects to be investigated. Now I hand over to Ilya.
Thank you, Manfred. I have the honor to say a little bit about different things that are going on in this catchment and what we have learned. One is the lab in the field, where we have real-time or almost real-time isotope and chemical analyses of both precipitation and stream water, which has shown that the concentration discharge relationships vary from event to event, and also allow us to look at different event water contributions during different events of different storm sizes and intensities. Next slide, please. Another part of the research is going on in a catchment that's called the Studiebach, a small one, where we focus on the connectivity between hill slopes and streams, asking questions on when these hill slopes connect to the stream. This work is based on a spatial network of groundwater well measurements, which can be interpolated to create maps of connectivity, as you can see in the top figure. We've also done lots of spatial analysis of the chemical composition of the groundwater and the stream flow and in this catchment and done a detailed mapping of the intermittent stream network, also to look at how streams connect during different events. Next slide, please. A lot of work, as you maybe saw in the drone video at the end, is also focused on bedload transport and torrent morphology, asking the question on how these streams change during storm event. On the drone video, you saw the basket sampler. In addition, there's acoustic sensors to measure bedload transport. There's been drone-based photogrammetric methods to monitor the channel and the sediment structure. This research has shown that it's not only the big events, the event size that determines how much sediment transport there is, but also how much sediment is available. And again, there is a link to what's happening on the hill slopes. Next slide, please. You may wonder, based on these measurements and examples of research, what we have. So in terms of data and infrastructure, there is meteo data and snow data and runoff data since 1969. This data was analyzed for this special issue in hydrological processes. In addition, there is bedload transport data. There is this spatial data on groundwater levels, groundwater chemistry, and also discharge. There is the high resolution isotope and chemical data that complements the long-term chemical data in these streams. And in addition, there were experimental plots to look at the nitrogen dynamics. Next slide, please. And in case you want to maybe look at some of this data, all the long-term data is available from the envi.ch webpage. You can search there and go directly to Optal. Some of the groundwater data is there. Some of the groundwater chemistry data is also there. Other data, we highly recommend that you contact the corresponding researchers who are happy to share it. For example, the bedload transport data or the isotope data. In addition, we hope that you will go and look at the website of the Alptal research, which is given here in the bottom, wsl.ch/Alptal, where you find the publications. You will find short explanations of the research that is going on, research that has been completed, and what the findings are. And above all, we very much welcome new publications, new collaborations. And in the next slide, there is a list with some key publications, but definitely also go onto the website where there are many more.
All right, thank you, Manfred and Ilya. Great overview of research there. There are two points to address so far. Rick Webb with USGS in Denver would like a quick summary of the methods for measuring bedload transport.
Yeah, I can say a few words about that. It's basically 4 methods. It's an indirect measurement of geophone measurements. It's a baskets that are running automatically into the stream when we have a flood. And then we have stones that we observe moving in the stream. And of course, we have measurement of the accumulated bedload in this big basin. So altogether gives us a lot of information on the dynamics and the totals.
Great. And then Joanna, who does some research in the Tatra Mountains of Poland, I think what she wants to know is, can you give a range of what are the old water fractions during flood events?
The majority of the water during flood events is old water, definitely. But new water fractions can be higher during very large events and at the peak.
Great.
And more than half. Yeah.
Thank you. Jamie and Julia, do you want to move on to the next, or?
Yeah, I think we're at time, but thank you very much, Manfred and Ilya. Okay, next up we have Breck Bowden, and we're moving to Alaska. Take it away, Breck.
Can you hear me okay?
Yes.
Okay, I've had to change to headphones, so background noise here. Thanks to the organizers for inviting me to this great session. I want to talk to you about what may be one of the shorter long-term records in the session this afternoon. Talk to you about some work being done by the Arctic LTER program in northern Alaska. This is an area that really wasn't very accessible until the 1960s or 70s, and the Arctic program, LTER program, operated by the National Science Foundation, funded by the National Science Foundation, and operated by the Ecosystem Center at the Marine Biological Laboratory, has been studying four basic themes since the early 1980s. So the tundra systems, lake systems, stream systems, and land water interactions. And I'm going to talk to you primarily about some of the streams and land water research that we've been doing over the last many years. Next slide. This research is being conducted. We're very fortunate to have the Toolik Field Station, which is operated by the University of Alaska at Fairbanks. You can see the location. Can you see my cursor? No? Okay. The Toolik Field Station is at the kink of the road. Right there, yes. The Toolik Field Station is about 130 miles south of the Arctic Ocean and Prudhoe Bay. The station itself, you can see in the picture in the lower right, is perched on Toolik Lake. And the watershed and landscape around the Toolik Station is in the picture that you can see there. Next slide. We're really fortunate that the station itself maintains a lot of extensive background data, geospatial data that you can see here, but also climate data going back about 30 years or so. In addition, the next slide, the Arctic LTER program has maintained its own database since the about 1983, 1984, for most of the things that we have been measuring in this area, as well as a number of collaborating projects. So if you were to simply Google on the Toolik Field Station, you would be able to get all of their data. If you Google on Arctic LTER, you can find all of this data. Next slide, please. What I want to focus on in the few minutes that I have here is the flagship experiment from the streams group, the streams component of the Arctic LTER, the Upper Kuparic River experiment. And the heart of this was a low-level phosphorus enrichment experiment that was conducted from 1983 until 2016. Monitoring is continuing in this, but the fertilization, the enrichment ended in 2016. This is the longest running intentional manipulation of an Arctic river that we know of, and there is there's a rich literature that has been developed about the influences on primary production, on secondary production, on fish population dynamics, and on the biogeochemistry in this manipulated river. The articles that I note here on the right-hand side of the slide are a series of a half dozen or so of kind of the key articles that summarize research at Toolik, and I just want to point out the last one there, which is a part of the special issue in Hydrologic Processes by Iannucci et al. That is a summary of this entire roughly 34-year record. Next slide. So Tim mentioned the increase in nitrate that they've seen in the Thames River study. I'm going to show you some similar data here, but we think we know why that's occurring. The area that we're in is an area that is underlain by continuous permafrost. This is permanently frozen soil. The surface thaws seasonally down to perhaps 10 to 20 centimeters, depending on the soil characteristics. But from that point down several hundred meters, the soil is below zero, remains frozen all year long, even during the summer. But those soils are warming dramatically, and this is a record from a recent paper by Biscobam et al. In Nature Communications that is showing the warming of permafrost boreholes across the entire Arctic. And you can see that in the upper left-hand corner there, the Arctic continuous permafrost zone is an area where those temperatures are increasing most rapidly and most significantly. Next slide. We predicted a long time ago that with that warming permafrost, we were going to see some changes in nutrient addition. And indeed, if you look at the nitrate graph, this is a decadal summary from the 1980s until the 2010s of nitrate concentrations going up very significantly over that period of time. And we attribute that to the at least to some thawing of the permafrost. But it was a big surprise to us that the phosphorus concentrations, which you see in that lower right blue corner, have actually decreased. We predicted that they were going to increase. I just want to point out to a very recent paper by Husser et al. In Freshwater Biology that does a pan-Arctic synthesis of nutrient changes over time, and notes that in many places across the Arctic, the phosphorus is decreasing. And we find that fascinating. If we can go to the next slide. One of the things that we had not thought about is that there is a lot of iron in these soils. There's particularly a lot of iron in the soils around Toolik Lake and the Kuparic River, and these have a high capacity to retain phosphorus. And so, next slide, we wonder whether the thawing permafrost, this is a slide from a recent paper by Kendrick summarizing some of the changes that we've seen in permafrost and how that has influenced the biology and the chemistry of the Kuparic River. He was the first to note this decrease in phosphorus in the Kuparic River, but at the time we hadn't really thought about the connection to iron. This is something that we know from lake biogeochemistry, but we've not really paid attention to it in Arctic systems, and we are wondering whether the decrease in phosphorus that we're seeing is a consequence of more iron being made accessible as a consequence of the permafrost thaw, and that this is a trend that we're going to see across the Arctic, and that may have some importance in the connectivity of the Arctic landscape to the Arctic Ocean and the ultimate delivery of nutrients that affect productivity in the Arctic Ocean. We think this is one of the most exciting areas of research for us in the future. And I'll just mention in closing an easily accessible source of information about all of the research that's been going on at the Toolik Lake site is this synthesis, Alaska's Changing Arctic, that was published as a part of the LTER book series. Thank you.
Great. Thank you very much, Breck. We don't have any comments or questions posted right now, and I think for the sake of timing that we should probably just queue up the next talk. But I do just want to point out maybe a couple discussion points that Breck could roll back on later. Is I had the pleasure of visiting this very remote site about 2 years ago, and I have to point out the obvious, the challenges of working in an environment like this, which is so remote and has such few facilities nearby, including power, sewer, good roads, or many roads. So it'd be very interesting to hear Breck's thoughts in the discussion part of this about how to maintain long-term monitoring under such dire circumstances as exist up there. But I think perhaps we should move on to the next speaker, though.
Yeah, okay, thanks, Breck. And I do want to point out there have been some questions in the chat that we haven't gotten to at the end of each talk, so we will get to them in the discussion at the end. Hold your thoughts. Our next talk is by Jasper Slingsby, and has Jasper been able to get on? So Jasper's in South Africa and was experiencing some power problems today and didn't think he'd make it. So he had the foresight to send us a recording of his talk. And I think that's what Julie is about to roll. We want to have questions
and
after this
thanks
one.
for coming to this seminar. And thanks to the organizers for inviting me. I'm going to start with a word to my sponsors. So I work for the South African Environmental Observation Network, SEON. It's a national facility aimed at supporting long-term ecological research in South Africa. And we operate as a distributed network of nodes around the country. And each node supports a number of different core sites looking at biodiversity, water, carbon, fire, climate, and so on. The nodes are generally associated with major biomes, but there are also 2 marine nodes. I'm an ecologist at the Fynbos node down the southwest corner, and currently the acting manager of the unit. So just a bit more about Fynbos. Fynbos is a hyperdiverse Mediterranean climate shrubland. It's also a global biodiversity hotspot. So 3% of the world's flora occurs in the Fynbos biome, and 2/3 of those of the species here are endemic to the Fynbos. So it's an incredibly diverse part of the world, botanically diverse part of the world. It's the richest temperate flora in the world. But obviously being a shrubland and being a Mediterranean climate, the 2 things that are predominantly scarce are water and timber. And those scarcities drove much of the kind of early politics of the region, and to some degree continue to be important features today. This obviously led to a question that was commonly asked across the drier regions of the world, which was what happens when you add forests to these open ecosystems. So what happens when you afforest Fynbos? Do forests increase or reduce the runoff or the water supply? And this is just a picture of one of our Fynbos mountain catchments. It is a invasion by the Monterey pine, Pinus radiata, and this is quite severe across a lot of our region. So this led to the government establishing the Uncertainties Forestry Research Center. The name has changed a few times, but that's kind of what's most commonly known as. And this was largely established around the Uncertainties multiple catchment experiment and an afforestation experiment, but it also supported research into various aspects of ecology, forestry, and so on. And there are a large number of publications that have influenced the major policies in South Africa around fire, water, vegetation, and so on. So looking at the afforestation experiment itself, this is the Jonkershoek Valley. It is a very steep valley with ranging from peaks around 1,500 meters down to 200 meters at the bottom of the valley, and then dropping off towards the northwest. The catchment experiments were done in 6 sub-catchments that face southwest, so they're kind of poleward facing. And what was done was they took one control catchment, which was predominantly Fynbos vegetation with a patch of indigenous forest, and then they had 5 treatment catchments, which were successively planted up with Pinus radiata every 8 years. So starting in 1940, the first catchment was planted up, then 1948, 1956, and so on. And this was essentially what's termed a multiple catchment experiment, but it's kind of like a repeated paired catchment experiment, if you like. And then obviously the valley was heavily instrumented with stream flow gauging weirs at all the major sub-catchments, and then rainfall recording stations all over the valley. I should just say this is all reported, and this map is from a manuscript that's in review as part of the Hydrological Process's long-term catchments special issue. This is just looking at a timeline of the site overlaid on the time series of stream flow recorded from the control catchment, the Fynbos catchment. So the Jonkershoek Forestry Research Center was established in 1935, and the experiment was started roughly 5 years later because it took a while to work out what to do and how to do it. And then it ran for 40 years. So from 1940 to 1980, they pretty much maintained the experiment. And thereafter, because the research center continued, they continued monitoring the equipment and recording all the stream flow and rainfall stations. In the mid 1990s, the Uncershoek Forestry Research Center was disbanded. And that entered what we've been calling the volunteer period, because essentially all data collection and maintenance during that period was maintained by former employees of the Uncershoek Forestry Research Center, either through kind of competitive grant funding that they managed to acquire, or just purely voluntarily on their weekends and the like. So a lot of data sets become a bit more patchy or end during this period. Fortunately, most of the major ones have continued. SEON only started in the late 2000s, and we took custodianship of the Uncershoek experiment in about 2009. And so we started instrumenting the sites with modern instrumentation 2009, 2010. And we've pretty much spent the last decade trying to make sense of the data records and all the various data sets, both hydrology and ecology. But this paper only reports on the hydrological or the hydrometeorological data sets. So the afforestation experiment was a success in that they got a result. And the result was essentially that, that afforestation severely reduces runoff in these catchments. I forgot to mention that there were actually several catchments catchment experiments run across South Africa. The other major one that's still in operation is Cathedral Peak, which is also operated by SEON. At Cathedral Peak, they looked at eucalyptus species, and then at Uncershoek, they looked at pine species, and both showed quite severe declines relating to afforestation of the indigenous vegetation. There's two curves here, because one is kind of under optimum conditions, so kind of wetter sites, and others are for drier sites. And then there have been various publications where they've scaled up these stream flow reduction curves to landscape levels. So here we have the Western Cape, and in another paper that's in review in the Hydrological Process, a special issue, we do this for the Fynbos region, where each polygon is a catchment, and we look at what is the influence of the invasive alien plant infestations on water resources from these catchments. And our estimate is that just for the city of Cape Town as a focal point, the catchments feeding the city of Cape Town have been losing between 20 and 40 million cubic meters per annum, which translates to 45 or 97 days of water supply. Bear in mind that in 2018, we got to within 50 days of running out of water. So that's a significant amount of water. And there's many reasons why this is actually an underestimate, which I'm not going to go into here. Other important features in this landscape and phenomena of interest, I'm not talking about any of the ecology per se, but although this ties in somewhat, with the major drought, groundwater has become a very important point. With the municipalities are investing in large well fields to tap into the groundwater to try and bulk up water supply to the municipalities and the agricultural areas. The mountains here are predominantly Table Mountain sandstone, and they support fractured rock aquifers that have considerable volumes of water in them. And then often you have water seeping out of the mountains, either along fault lines or geological contrasts, as you can see here. And so in this case, this water comes out of along this contact, and it forms a stream that then feeds a kind of a perched wetland. And when that overflows, it goes down this valley, which actually is heavily forested at the top because of this extra water supply. And so we're concerned about what happens when we pump lots of water out of the system for the resource itself, but B, what happens to the groundwater dependent ecosystems and species. So that's something that we're trying to monitor into the future. Another major component is this phenomenon, which is southeast cloud. Cloud and fog, what does it mean for evapotranspiration and for direct water inputs, and what does that mean for the ecology and the hydrology of the region? So in updating the site as a modern kind of global change observatory, we've been adding various additional instrumentation, eddy covariance, various fixed photography, and fog observations. But I'll leave it there, and you're welcome to explore our website for additional information about the site. Thank you very much.
Thank you very much, Jasper, for that pre-recorded talk. I want to point out that Jasper is communicating with us via the chat right now, and he's actually held or responded to several questions already. Again, they're in the record for you to review. I think we should probably move on to our next speaker just to have enough time for Irina to complete her thoughts and for us to have a nice final discussion. So with that, please do visit the chat. We'll try to keep responding to all your questions as we can. Thank you very much.
Thanks, Jasper. And so our final speaker this afternoon is Irina Creed, and she'll be speaking about a whole bunch of catchments.
Thank you sincerely to the organizers for creating this wonderful series on catchment sciences. My goal today is to put a spotlight on what we call vulnerable waters that are often invisible and therefore ignored, as illustrated in recent publications from members of our own community that have introduced the terms such as cryptic wetlands and streams incognito. Next slide. We define hydrologic resistance as a catchment's ability to absorb disturbances such as floods and droughts while maintaining or quickly recovering hydrologic functional traits such as storage, fill and spill, and its synchronicity between precipitation and discharge. Next. We explored the importance of vulnerable waters in conferring a catchment's hydrologic resistance to and recovery from disturbances at national scale. So today I'm going to speak about the entire United States. Next. We argue that vulnerable waters punch above their weight in terms of their ecosystem functions and services, as shown in the blue map for headwater streams and the green map for wetlands outside of floodplains. In our 2017 paper, we estimated that intermittent streams provide almost $16 trillion per year, and non-floodplain wetlands provide about $700 billion per year in ecosystem services. Next slide. However, governments, as in the US as well as across the globe, are not adequately protecting these vulnerable waters, and that places the ecosystem functions and associated services at risk. And so scientists are needed, such as catchment scientists here, to provide evidence for in support of policies to slow down the degradation and destruction of these vulnerable waters. Next slide. So today I'm going to talk about a data set that we looked at in terms of catchment hydrologic resistance. We measured hydrologic resistance by the degree to which discharge, which is Q, is coupled with precipitation in P. In other words, the PQ correlation. So catchments that store water and release it gradually to the stream have a low PQ correlation and therefore a high resistance, indicated by the green dots. But in contrast, catchments that do not store water but release it quickly to the stream have a high PQ correlation and therefore low resistance, indicated by the blue dots. Today I'm focusing on vulnerable wetlands, and I hypothesize that catchments with a high proportion of vulnerable wetlands have a high hydrologic resistance. Next slide. For our analysis, we focused on the wonderful data set provided by CAMELS, the Catchment Attributes for Large Sample Studies. The CAMELS data set uses distributed hydrologic simulation modeling to produce hydrologic signatures for hundreds of catchments in the US. I focused on 530 relatively undisturbed catchments for almost 30 years of data to understand the importance of these vulnerable wetlands to hydrologic resistance. Next slide. So I considered both what I call distal factors and proximal factors. For the distal factors, those were things that influence the catchment's water balance. And so I placed catchments into one of 4 domains based on water availability as defined by the theoretical energy and water limits, as well as water synchronicity, whether the precipitation and temperature are in phase or out of phase. Next slide. I also considered factors, and these are the proximal ones, that influence the wetland storage capacity, its type, and its connectivity to the nearest stream. In our conceptual model that we published on the left, Travel times are shortest for wetlands with persistent surface connectivity. These are colored in green and designated as high connectivity wetlands. Travel times are intermediate for wetlands with episodic surface connectivity. These are colored in gold and designated as moderate connectivity wetlands. And finally, travel times are longest for wetlands without surface connections. These are colored in red and designated as low connectivity wetlands. I used the classification scheme on the right to map the effective travel times for almost 7 million wetlands to down gradient stream segments across the conterminous US. Next slide. So here are our findings. I'm going to focus first on catchments that are in phase. And again, this is where the peak precipitation and peak temperature are in July, in domains that are both relatively dry, denoted on the map in the yellow dots, and wet, denoted on the map in green dots. In each box, catchments that fall to the left of the dotted line, the wetland connectivity metric is negatively related to the PQ correlation, and that's our indicator of a higher resistance. Here, as predicted, low connectivity wetlands conferred higher resistance, i.e. they fell to the left of that dotted line. Next slide. This has the same layout as the previous one, but on this one, I'm focusing on systems that are out of phase, where at the extremes, peak precipitation is in January and peak temperature is in July, in domains that are both dry, and these are denoted by the red and yellow, and wet, and those are the ones denoted in blue. But here was a surprise, not as predicted. We found that it was actually high connectivity wetlands that conferred the higher resistance. Next slide. So our key findings are as follows. For in-phase systems where peak precipitation and peak temperature occur at the same time, these low connectivity wetlands, these vulnerable waters, may be functioning as a piston where infiltrated water that is protected from evapotranspiration makes its way to the groundwater table, where it pushes water to the outlet, resulting in an increase in base flow and a more stable discharge over time. And this is our measure of hydrologic resistance. But for out-of-phase systems where precipitation and temperature peak occur at different times, low connectivity wetlands have no effect on discharge. And it's the high connectivity wetlands that may be functioning as storages, resulting in a decrease in peak flow and more stable discharge over time. And again, ultimately, the higher resistance. So in conclusion, while we were able to advance our scientific understanding to support the protection of these vulnerable wetlands, we still need further developments in our conceptual models so that we can reconcile our predictions from our observations, especially in these systems that are out of phase. And so thank you, that's the end. I'll leave the conclusions just to be read.
Thank you, Irina. We can handle a question or two on Irina if somebody wants to put that. Oh, we just got one in. So how did you select the 500 plus catchments from the 600 plus catchments in the CAMELS data set?
We specifically picked catchments that were relatively undisturbed because we really wanted to not have our results conflated with disturbances that were more human-based, such as agriculture, land development, etc. So these were relatively natural landscapes, and really the signal that we were looking at for disturbance were climate extremes, such as floods and droughts.
Thank you. No more direct questions for Irina, so I think I'm going to pivot here.
Whoa, Steve, there's one from Larry Band. I believe this is for Irina. Have you distinguished recession flow characteristics for these different classes?
No, Larry, thanks for the question. At this point, we really focused on annual metrics for total water year, precipitation, discharge. Clearly, this is just the first step, and we can look at much more refined metrics of resistance and resilience moving forward by looking at the fullness of the discharge hydrograph.
Great, thank you. So I think it's time to engage with the full panel or us conveners. Start putting your discussion points forward, but I think we've had a great one that I'm just going to address to any of the panelists or conveners who want to jump in here. But this is a very broad question. what do you guys and gals view as the 1 to 3 most important variables to measure at long-term sites, especially if funding is limited? Any takers? Maybe I'll jump in. So I'm part of the USDA Forest Service, and we've operated long-term catchments for 80 plus years, and Wagon Wheel Gap in Colorado was one of our experiments back in the 1920s, I believe. I think some of the most important things that we can measure are the basic meteorology and some metric of water, whether that's stream flow, where there's streams, or water tables, perhaps where there's peatlands or lakes. And then maybe some other metric of a driving force, such as air temperature. That's what I would throw out. I welcome other comments here.
I'll just pitch in and say that long-term records of precipitation and also temperature are really helpful in many cases where you don't really have a control watershed, or the control is out of control. And so you can use the precipitation data as a reference, or the climate, in fact, as a reference to look at change.
I'd like to jump in and respond to Mike's comment in the chat, and perhaps this is my bias, but I think that with the struggles to maintain LTERs individually, we need to show the power in numbers, and to do more of these kind of comparative catchment analyses to show where we can get unifying hypotheses that can emerge, or generalizations and scaling ideas that can emerge. And so would love to see much more cooperation amongst the sites, not to say that we're not cooperative, but to create opportunities that we could do some of these comparative analyses.
Yeah, and
I might just build on top of what Arena's just said, and the question about what should we measure. You know, when these studies start off, there's this question that's often being asked, right? And so there's particular metrics that are being measured, and they might be being measured in different ways in a limited number of places. And to Arena's point, for us to be able to make these comparisons, for us to think to the future about you know, how we can make these measurements more comparative for these longer term syntheses is a real challenge, and something that we need to pay attention to. That will create these opportunities for higher level spatial syntheses.
Yeah, absolutely. And we have to be careful too. We have so many catchment studies out there with different measures and different ecosystem properties. We can't assume that every watershed is going to fit every analysis, and that's fine. If your catchment isn't relevant to the hypothesis, it will be to another one that somebody else will throw out as a synthesis topic. So it's really important just to work together where we can, and to foster the coordinated and consistent measurements wherever possible. But not everyone can measure everything at all times, and that's fine. We just want you out there. We want you measuring things at your site in the context of your questions, and if we can pull it together, that's really important. I want to bring in another aspect of the synthesis question here, and somebody early on asked essentially, where are the data and how do we access them? And that's a loaded question, because sometimes the data aren't available. Sometimes they've been lost to history. But then again, there are many repositories, and it's becoming more the norm for us to share data. And this is where it swings back into the special issue of hydrological processes that Jamie and I and Julia and Theresa and others who are probably on this call are trying to facilitate that. We have nearly 60 data note type articles that are going to be coming out, if all are accepted, about 60 data notes. And that's the express purpose of the data note, is to define the data sets, define the catchments, and to tell people where you can get the data. You can't just say we collect data and not make it available. The whole point of this is brag about what you have measured and where people can access it. So I would say that's one outlet. Other places like this question was actually directed to Breck, I believe. the Arctic LTR and all US LTR sites are all part of the NSF Environmental Data Initiative, which is also part of Data One. So there are repositories out there. You know, each site has their own individual repository, and then they're oftentimes aggregated into these other repositories. So I think that's key as we think ahead, that there are a lot of data available. A lot of us are working to advertise those data sets. Now we need the brilliant minds that are represented in this panel and on the rest of this call to pull together the ideas and then to work with all of us to address the big questions or even the long-term questions that we just haven't been able to answer yet.
If I can add on to your wonderful statement, Steve, and that is, my experience has been, even though we have many of these LTERs, they're still working relatively in silos. A real opportunity for the special issue and the 60 data notes is now that people have gathered their data to be ready to publish, that maybe we could come up with standardized templates. And again, it gets back to what Breck is talking about standardized protocols that we could allow for this catchment comparison and synthesis work to happen. It's relatively easy for more of the physical parameters. It's really tricky for the biogeochemical parameters. But until we do that, I don't think that we're really putting a spotlight on the importance of what catchment scientists do.
So we have a couple of comments. Kevin Bishop would like us to address how do we develop a measure of total storage so that we can evaluate uncertainties in water balance terms. Any thoughts on that? While you ponder that, Kevin is also pointing out some other, Kevin is being quite vocal today, so thank you, Kevin. Nice to hear from you. Kevin and Jasper had a little bit of a discussion about what are the effects of afforestation or tree growth on landscapes. And it's been contested in the literature about whether there are positive, negative, or neutral effects. There's some ideas worth reviewing in there. But I think he's trying to point out in a comment about some research in Ethiopia that there is a strong belief that trees are conducive to water flow and that native species make a difference. And again, if anyone wants to pick up on any of these points, I'm just trying to throw out a couple discussion topics.
I had actually put a question to Jasper about the importance of cloud water inputs as you shift from grassland systems to the Pinus radiata that they're studying in their system. And I'm not asking for an answer to that question necessarily, but the point of needing to study and quantify different aspects of the system as they change, as the vegetation system changes, is something we need to pay attention to in longer term studies, and components of the hydrologic cycle that we might not have paid as much attention to. I'm really glad to see that they're focusing on cloud water inputs in the Jaggerstock, I may not be saying that correctly, watershed.
Can you hear me?
Yes.
Sorry, I'm doing some crazy technology juggling here. So here it's long been known amongst botanists and ecologists for being very important for the vegetation, but our understanding of how it affects the hydrology is not well understood. There's some early papers from the 30s about influence on daily daily cycles and evapotranspiration, but we don't actually know if there's actual input into the system beyond just wetting of leaves kind of thing. But yeah, so these are the things that we're trying to get into, and we've actually got some isotope studies going as well to see if we can actually see water coming in from fog or cloud. But yeah, it seems that the input itself would be minimal. It's mostly a cooling effect and an evapotranspiration effect, because we've had kind of soil moisture sensors under our fog collectors, and we'll get lots of fog on the collector, but not much soil moisture change.
Yeah, Jasper, you may already know about, or if not, be interested in a long-standing debate that's been going on about the relative importance of cloudwater inputs at the Glendhu forest, catchment forest in New Zealand, as it transitions from tussock grassland to radiata pine.
All right, we're honing in on the end here. I think Mike Kirkby poses a really important question, and what he says is, should or does the data proceed or follow the critical questions? And again, I think the answer is sometimes it does, but when we're in a world of iterative science or serendipity from monitoring allows us to address questions. I think they're certainly part of the puzzle. So I'm not always concerned that we don't have the hypothesis known when we start these watershed studies, but I think the monitoring over long term just allows so many other opportunities to address pressing questions, long-standing questions, or just reevaluation of, did we get it right the first time? Other panelists, please, again, what's the importance of not posing the question and not having the hypothesis before a long-term study is established versus post hoc development of those hypotheses and or questions?
Yeah, this was Tim's whole point. Why don't you go, Tim? You had a question or a comment.
Yeah, I think the other side of the coin is, I suspect the people who fund these projects will often feel that, well, surely you've done this for 50 years, you must have enough data. And I think our response should be that new hypotheses will arise because new issues and pressures arise. And so the fact that things change and that there are new threats, I mean, the climate emergency, biodiversity crisis, all these things mean that there are new questions, and that it's hard, I think, to argue that, oh, well, we've got 50 years of data, we can stop. We've really got to argue for and be able to demonstrate the value of having these data sets from which new ideas arise and or can be tested. So I think sometimes the data comes second, but sometimes they come first and the ideas come later.
Yeah, that's really good point. And there's serendipity, stuff you find out just from monitoring. And then there's the point of monitoring after policy change, like with the acid rain funding in the US. So much money went into that in the 80s, and then Clean Air Act passed, which was great, but then there was no funding to look at, how good it was. So yeah, great point on monitoring. I love some of the quotes you had in your talk, Tim. So about time to wrap up here. I just wanted to say that we'll be putting out a more full schedule than you've seen so far with all the participants listed. We're just kind of juggling to get the final list, but that's being finalized now. We'll get that out shortly. And a plug for next week, we'll be dedicating the session to hydrology. Jeff McDonald's going to give a kind of a plenary talk on, the importance of hydrology to catchment research. And, I feel that hydrology is really kind of the cornerstone of a lot of our catchment research, and that the biogeochemistry, really has to have a foundation on hydrology to understand how solutes are moving. So thank you very much, everyone, for participating, and I look forward to seeing you back next week.
May I make a quick plug, Jamie?
Sure, go for it.
So we flashed our global map of catchment studies at the beginning of this. I'm missing a lot of sites. If you know of them, if yours is one of them, please email me, Stephen Sebestyen, and let me know the geographic coordinates of the research catchment and the site. I would greatly appreciate making that map better. It's got a lot on it. It needs a lot more. So thank you. Thank you for everyone participating and all of our panelists for being here today.
Great. Thanks, everyone. Bye-bye.